Hi, my name is Isaac Joseph, and today we are going to be talking about the Box-Mueller transformation. So we have our question here where we are asked to use the Box-Mueller transformation to take our uniform independent variables and transform them into Gaussian normal variables. So our first part of our question, I'm just going to be explaining really quickly the Box-Mueller transformation. It can be visualized as a system where we input our uniform variables here along with our desired means and our desired variation, and we're able to output our Gaussian random variables here. And looking at the graphs, our input uniform variables would look something like this as a PDF, whereas the Gaussian distributions would look more like this graph over here. And when they're normalized, we know that the mean, or the mu, is going to be equal to 0, and we know that the sigma, or the standard deviation, is going to be equal to 1. So given this equation, we already know the equation for the z-score of a normalized Gaussian distribution is going to be z is equal to x minus the mean all over the standard deviation. So the first part of this question asks for us to find z1 and z2 in terms of x1 and x2. So in order to do that, all we have to do is take these equations that were given for y1 and y2 and rearrange them into this form to isolate for z. So that's exactly what we do here. We subtract mu from both sides, and we're able to take that variance out of the square root by making it into standard deviation, and we can divide that from both sides, and this is what gives us our relationship for z1 and z2. And we know that these are going to be verified by their range, because we know that the range of this portion is going to be 0 to infinity, because x1 and x2 span from 0 to 1. So ln of anything 0 to 1 is going to be negative infinity to 0. And then that is going to be multiplied by negative here. So that is why we have this as the range for this section, and then sine of x2 is just going to be minus 1 to 1, which gives us our total range of negative to positive infinity for z1 and z2. So the second part of this question asks us to isolate for x1 and x2. And actually, when we're isolating for x1 and x2, what we're going to be doing is we're looking for x1 and x2 in terms of z1 and z2. We want x1 in terms of z1 and z2. Same with x2, we want it in terms of both of them. So we know that we need to relate these equations in order to find them. And x1 we can see is inside of a ln term. So we're taking the natural logarithm of x1. So what we're going to do is, first of all, we need to isolate for x1. That's the most important step here. So we're going to just add these two equations together. So we have z1 plus z2 is going to be equal to this plus this. And we're going to square both sides of the equations, as you can see, in order to get rid of the square roots here. And when we do that, we can see that z1 squared plus z2 squared is going to be equal to this plus this all squared. And we can take out this common factor of minus 2 ln x1. So we factor out the this common factor, and we're left with, in the bracket, cos squared plus sine squared of 2 pi x2. And we know, given our trig relationship knowledge, that cos squared x plus sine squared x is just 1. So this is going to simplify out and become a lot easier for us. So we're just going to divide negative 2 from both sides, and we have ln of x1 is equal to all of this. And in order to isolate x1, we just have to raise both sides to the power of e, or raise e to the power of both sides. And we are able to isolate x1 and find our equation for x1 with respect to z1 and z2. Similarly, for x2, we're going to be doing the same process, but we need to isolate for x2, which is inside of this trig relationship here. We can see, just looking at the two equations, we need to relate these two equations, and both of them have this common term we need to get rid of. So what we're going to do is we're going to divide z2 divided by z1. And that's exactly what we do here in order to let these two common factors cancel each other out. We do z2 over z1 on purpose because we have a sine and a cos term, and we know that sine divided by cos is going to be tan. So by doing this, z2 over z1 is equal to the tan of 2 pi x2. Now to isolate for x2, all we have to do is take tan inverse of both sides. So we have 2 pi x2 is equal to tan inverse of z2 over z1, and by dividing both sides by 2 pi, we're able to isolate for x2 as well. Finally, this question wants us to verify the joint PDF of x1 and x2. Given the marginal PDFs of x1 and x2 and the information that x1 and x2 are independent of one another, we can do this very easily. A uniform variable such as x1 or x2 will have a marginal PDF that looks something like this, where the PDF goes to a height of p, and we know that the boundaries are between 0 and 1 for x1. So we also know that for a uniform distribution, the integral of the PDF is going to be equal to 1. So we can use this relationship and find that this p, or this maximum of the PDF, is going to be equal to 1. So doing this integral, we found the marginal PDF of x1, which would be the exact same as the marginal PDF of x2, given that they have the same conditions and they are both the same type of variables. So we have these marginal PDFs here. We found it for x1 and for x2. And we know that the joint PDF for two independent variables is going to be the product of their marginal PDFs. So we have their joint PDF, which is just going to be the product of these two marginal ones. And since it's just 1 and 0, it's going to be the same thing. However, we just pay attention to the bounds here because they do have the same bounds, but this joint PDF is now related to the bounds of both of those uniform variables. So for our next part of this question, we are asked to find the joint PDF of Z1 and Z2. So we already have the equations for x1 and x2 as functions of Z1 and Z2, and we also have their joint PDF. And we want to find the joint PDF of Z1 and Z2, and in order to do this, we need to use a Jacobian matrix. So this matrix is a very important relationship to know because the determinant of this matrix is going to help us use these three pieces of our puzzle in order to find this last piece over here. And we can do this with any different variables. It doesn't need to be the Z-score. It just needs to be that we have these pieces in order to find this piece. So we're going to start off by solving to find the terms of this Jacobian matrix, which are just going to be the partial derivatives of x1 and x2 with respect to z1 and z2. So we start off by recalling our equation for x1 in terms of z2 and z1. And we find first the partial derivative of x1 with respect to z1, which is simple. We just take the derivative with respect to z1, the partial derivative, and we are left with minus z1 times e to all of this, just because it is just a simple partial derivative where we have e to the k is going to be equal to e to the k times k. And we also have the exact same thing for the partial derivative of x2. And actually, just let me move my face over here so you guys can see this over here. We have our partial derivative formulas over here for x1, and this should actually be a 1 here. So this should be a 1 right here. It kind of looks like a 2 there, but I don't want to cause you guys any confusion. So it is going to be a little bit more challenging to find our partial derivatives for x2. We recall that our equation for x2 includes this tan inverse relationship over here. Okay, so in order to take our partial derivative of x2, we're going to be using our u substitution here. So we're going to make the contents of the tan inverse relationship equal to u, and we know that tan minus 1 of u all over du is going to be 1 over 1 plus u squared. So using the partial derivative here, we can break this down into this form. So we have, with respect to z2, we have 1 over 1 plus z2 over z1 squared, and we're going to multiply that by 1 over z1, which is going to be the remainder, and we have our partial derivative of x2 with respect to z2 here. And similarly, we do the exact same process over here in order to get the partial derivative of x2 with respect to z1. So now that we have all of the pieces of our Jacobian matrix, we're just going to plug those in. So it is super important that we plug them all into the right places, and that's what we do over here. We're making sure that we have all of these in the right spots, and what we're going to do is take the determinant of this matrix. So if you recall, the determinant of this matrix is found by multiplying this term by this term and subtracting the product of this term and this term. So what we do here is exactly that. We multiply these first two terms together. We're going to multiply this guy over here with this guy, and that's going to give us this first term, and we're going to subtract the product of these two terms over here. And the second line over here is the exact same thing. All we just do is expand these brackets by multiplying these two functions together. And we notice that every term in both of these cases is common between both of them. So what we're going to do is we're going to factor all of our common terms out over here, and that's just going to leave us with z1 squared plus z2 squared, which is just going to be these guys over here, and those two can actually cancel out with this denominator here, and this leaves us with our determinant being this guy right here. So in order for us to find our joint PDF of z1 and z2, the equation for this is going to be, we're going to multiply the determinant, the absolute value of the determinant of that Jacobian matrix, multiplied by the joint PDF of x1 and x2. So this joint PDF is only going to be 1 and 0. So we know that this is going to be the absolute value of our Jacobian matrix. So this is going to become a positive sign right here. So this is going to become a positive 1 over 2 pi. And so it's going to be equal to this at 1 and 0 otherwise, in between 0 and 1. So we have our joint PDF of Z1 and Z2. And in order to prove that Z1 and Z2 are independent and normalized Gaussian variables, we're going to come back over here and just take a look at this equation that I have right here, which is going to show us the PDF of a normal distribution. So this is the normal formula for the PDF of a normal distribution. And when we have a mean of 0 and a variance or a standard deviation of 1, this is going to simplify because our sigmas are going to be 1 and our mu is going to be 0. So this is just going to simplify over to 1 over root 2 pi times e to the minus x squared over 2. We know that e to the a plus b is equal to e to the a times e to the b. So we're able to break this down into z1 squared over 2 and minus z2 squared over 2. And we're also able to break this term 1 over 2 pi into 1 over root 2 pi times 1 over root 2 pi. So by doing that, we're able to separate this joint PDF into two marginal PDFs. So this gives us the marginal PDF for Z2 and Z1 here. And as we can see, by multiplying these two together, we would get our joint PDF. So as we discussed earlier, that means that Z1 and Z2 are going to be independent because their marginal PDFs can be multiplied together in order to get their joint PDF. And we can also observe that their marginal PDFs are in this standardized form for the PDF of a normal standardized distribution. So we can also say that Z1 and Z2 are Gaussian normalized distributions for their PDFs. The last part of this question asks us to prove that the Y1 and Y2 Gaussian PDFs are again normalized with their mean and standard deviations or variances given here. So what we're going to do is the same process for Z1 and Z2. I showed the steps here for Z1, but it's the exact same for Z2. We're just going to take this, this Z1 equation that we've already found, and we're going to isolate for Y1. So we have this equation where we have Z1, which is going to be a random variable, which is going to be multiplied by the sigma value. So this is going to be a scaling factor here. And we also have a shifting factor here of the mean, or the mu. So to start off, we're going to try to find the expected value of Y1, and we're going to be doing this through this relationship here. So we're going to do exactly that right here with our scaling and shifting values. We're going to multiply this by the expected value of Z1 and add the mu of Y1. And we know the expected value of Z1 is going to be 0 because, as we previously proved, this is going to be a 0 right here. So this is just going to simplify down. The expected value of Y1 is just going to be the mu of Y1, or the mean of Y1. We can continue to find the variance of Y1 using this formula over here. And the important part here to note is that the scaling factor becomes squared in the variance. And the other thing is that when we have a shifting factor in our variance, it goes away because it does not matter to our variance. Because essentially our variance is going to be representing the spread of our data. So I'm just going to move my camera over here. But our variance is going to represent the spread of our data. So if we add a shifting factor, that means that every data point is going to be shifted up by a certain number. So if we are shifting up by 2, the spread of these data points does not change whatsoever. So whenever we have a shifting factor in our variance equation, this guy is just going to go straight away and is not going to be used in our calculation here. So we're going to square the sigma value. We know that the variance of Z1 is going to be 1, as we had previously calculated. So the variance of Y1 is just going to be sigma squared of Y1. And so using this, we have proved that Y1 is a normalized Gaussian distribution, and it's going to be the exact same steps to prove that same relationship for Y2. Thank you.